Hello everyone, I am Ithihas Madala, one of the authors of the paper Motor Imagery based Multimodal Biometric User Authentication System using EEG. I, along with Akshay Valsaraj, will be presenting this paper today. First, I will give a brief introduction and talk about the current developments in this field. Then, I will discuss the data collection and pre-processing techniques which we incorporated in this study. After that, Akshay will take over and discuss the feature extraction tools, machine learning algorithms, and performance metrics used to assess our model. Finally, we will present the results of our model and end with a brief discussion on the future prospects of this technology. BCI needs no introduction. It is one of the fastest growing research fields with companies like Neuralink, Emotive, Neurable, etc. racing towards advancing in this field. And for the past few decades, BCIs have been extensively researched for its application in rehabilitation. However, in recent years, BCIs have emerged as a potential biometric user authentication system as well. There are many biometric systems in the market already, and are broadly categorized as physiological and behavioral biometric systems. Some of the most common biometric systems are face recognition, fingerprint recognition, retinal and iris scanning. But these are already available in relatively inexpensive hardware like smartphones. However, these biometric systems can be fooled with the help of specific tools designed for a particular system. For example, anti-surveillance masks for face recognition, similarly voice coder for voice biometrics, contact lenses for iris-based authentication, and fingerprint films for fingerprint recognition. This is why we need a new foolproof system, and BCI fits the bill perfectly. In the past, EEG-based authentication systems have been designed using visual stimuli in combination with relevant event-related potentials as a characteristic identifier. In some of the simplest cases, eyes closed, eyes opened, and resting state conditions have also been used for authentication purposes with spectral coherence connectivity as a feature. Past studies have also demonstrated authentication systems using rapid serial visual presentation or RSVP. There are also systems that used breathing, simulated finger movement, sports activities, singing, passage recitation, audio listing, and color identification as various parameters for authentication. Our study specifically focuses on motor imagery or MI. Motor imagery is the task of imagining a movement without physically executing it. The basic task of motor imagery leads to a unique and characteristically consistent change in the neural signals of a person, and hence this can be used as a secure identification method in which it is hard to mimic identity. As compared to the BCI response created by visual or auditory stimuli, motor imagery is beneficial as it does not require any stimulus and does not lead to substantial fatigue. It is also compatible with subjects who suffer from severe motor disabilities. In our study, 25 normal, healthy volunteers, 3 female and 22 male, aged between 18 to 25, with an average age of 20 with normal or corrected to normal vision participated in the study. The participants were student volunteers for their availability and interest in the study. None of them had a history of neurological or psychiatric diseases. All subjects were informed about the testing procedure and signed a written consent. A full explanation of the experiment was provided to all the participants, and the research group thoroughly explained the protocol to the volunteers. The subjects were seated in a comfortable chair, resting their forearm on a wooden armrest. A computer screen was used along with an in-house psychopy stimuli cue for the tasks, while the subject's EEG was recorded, and the study was approved by the Institutional Ethics Committee. The experiment was designed to acquire EEG signals corresponding to 4 real actions, 4 corresponding MI, and the baseline signal, which was the resting state. The signal was acquired using the EGI EEG headset, which has 32 channels with a NetStation toolbox. The experimental setup allows us to record EEG signals while simultaneously labeling the data with event markers, which were designed using an in-house system. The 1020 International Electrode Placement Protocol was used with sampling rate of 250 samples per second. The data was acquired continuously for the complete duration of the experiment and later segmented according to the event markers. This arrangement resulted in 8 possible events for the subject, and this stimulus cycle with rest state for 3 seconds, get ready state for 2 seconds, and the visual cue for 5 seconds was repeated 4 times in one set. Each set had pseudo-randomized combinations of 4 events out of 8 mentioned in the slide. Each subject underwent 24 sets in a single session, giving 12 data segments for each of the 8 events. Baseline was considered as a 5-second segment, including both rest and get ready segments. The whole experiment lasted 16 minutes per subject. Now coming to the signal processing, it was done using Python and MATLAB engine. The whole data was filtered using infinite impulse response (IIR) Butterworth bandpass filter with a lower frequency limit of 0.1 Hz and a higher frequency limit of 70 Hz. Along with that, we used a notch filter at 50 Hz to filter out relevant frequencies of interest and to remove the electrical line noise. As motor imagery rhythms are observed in motor cortex regions, data from electrodes C3, C4, F3, and F4, according to the 1020 system, were used for analysis. The 15 datasets with more than 50% bad epochs due to incomplete experiment or unstable data resulting from subject fatigue and noisy data due to movements were not considered in further analysis. The exclusion was carried out by visual inspection of the epochs. Since noise is a high signal frequency produced due to external interference, while the signal of interest is usually of low frequency, wavelet transform can decompose a signal very effectively into approximate and detailed coefficients, which contain most of the noise. The detail coefficient's size can then be significantly reduced by thresholding. Coming to the specifics of the filter, the SIM9 wavelet was selected as previous studies have shown that it has a better cross-correlation with EEG signals of motor cortex. Signal denoising of the observed signal has three important steps. 1. The signal is converted into a wavelet packet transform. 2. The coefficients are shrunk by either hard or soft thresholding. Hard thresholding leads to a loss of important features of the signal. Hence, soft thresholding was used such that the coefficients are not reduced significantly and the signal information is not lost entirely. Third, the modified coefficients are transformed into corresponding inverse wavelet packet. Now that's about the signal processing and denoising. Next, I'd like to hand it over to Akshay. He'll discuss the feature extraction. Thank you.
Hello, I'm Akshay and I'll be talking about the feature extraction and the results and conclusion of our project. So one of the main aspects of a brain-computer interface is to process the signals and extract the most important features. In this project, we use power spectral density. It's a function that extracts the strengths of the variations in the energy and it captures the signal dynamics in the frequency domain. And therefore, it's proven as an effective feature extraction technique for motor imagery-based BCI systems. Power spectral density is calculated using various methods. And in this study, we use Berg's method, there's even Welch's method, and many other methods. But the main reason why we selected Berg's method was because when it's implemented on time series data on iterations, and it can be used to find a reflection coefficient that helps in reducing the forward and the backward prediction errors using the autoregressive models. And many of the papers that we referred had used Berg models. And now we're talking about the various classification models that we touched upon. We went with 4 different models: K nearest neighbors, naive-Bayes, random forest, and support vector machines. So in the case of K nearest neighbors, it calculates the Euclidean distance of the value to the nearest K values from the trained sample and then classifies it to a particular class, which is the most common among the different K neighbors. For example, if I take the value of K to be like 5, so it selects the 5 nearest neighbors of the value and then it assigns it to the neighbor which has the most count in the domain, which means which has the most probability of it being in that group. So in the case of naive-Bayes, it calculates the probability of a particular value belong to a particular class and classifies the value to that class of the highest probability. Naive-Bayes is highly dependent on the Bayes theorem and we have used that for this model. So in the case of random forest, it creates multiple decision trees by taking various combination of classes and samples from the training set. Decision trees are similar to flowcharts in terms of structure. A node represents a test or an attribute, and each branch of the node holds an outcome of the test, and each leaf node is a class label. So coming to the last model that we used was support vector machines. So SVMs are based on the idea that the classes can be separated linearly using a hyperplane to maximize the spaces between the most classes. For example, if in the case of logistic regression, we use a straight line to like separate the classes, but in this case, we're using a hyperplane. So that's the only difference. And like there are many different kernels available for SVM, such as Symboid and polynomial, but we use the RBF kernel since it was found to have better performance compared to the other kernels that we used. And every authentication system has a performance evaluation metric. So in this verification systems, it consists of 2 subjects, which are the clients and the imposters. And our testing data set comprised of 20 data points corresponding to 10 subjects. And it was split into two parts, 2 clients and 18 imposters. And an algorithm can either predict correctly, that is either true positive, that means it correctly identifies a client, or true negative, which means it correctly identifies an imposter. Or any algorithm has its own defects, and it can make errors. For example, it can make a false positive error, which means it incorrectly identifies the imposter as a client, or a false negative error, which means it incorrectly identifies a client as an imposter. And then we combine all these values in another metric known as a false acceptance rate, which is the false positive divided by the false positive plus true negative, and false rejection rate, which is a false negative divided by the false negative plus true positive. And we need one more metric so I can combine both the false acceptance rate and the false rejection rate. So we use DCF metric, which is known as a decision cost function, and it's calculated by the cost of the false negative into the probability of the client into the false rejection rate plus cost of the false positive into the probability of the imposter into the false acceptance rate. So in this case, we consider the cost of the false negative and the cost of the false positive to be 1. And the probability of client was given by 2 by 80, 2 by 20. And the probability of the imposter was given by 18 out of 20. And the false rejection rate and the false acceptance rates were calculated by using the above formula. So now that I'll be sharing the results that we obtained. As you can see from the tabular data, we calculated the 4 different actions for each imaginary and real actions, and we calculated the cross-validation test and the test accuracy for both the imaginary and the real actions. So by just glancing through the tables, you would have seen that the random forest gives a higher average than compared to the other models. And we have used this model for the other further analysis, because since it gives the most best results, gave an average of about 92% in the case of cross-validation accuracy and 87.5% in the case of test accuracy. That's in the case of imaginary. But in the case of real action, it gave about 91.25 accuracy in cross-validation and 86.25 in the case of test accuracy. So we can see that it performs the best compared to the other models, and the least was performed by XVM. It gave only about like test accuracy of 68.75 in real actions and 70 in imaginary actions. So this validates that the proposed system is quite efficient for people who have lost their motor capabilities. For example, if we take the case of imaginary actions, you'll see that it has a better accuracy compared to the real actions in the case of test accuracy. So this would be a huge advantage for people who have motor disabilities. And so after that, we calculated another table where we calculated all the false acceptance rate and the false rejection rates. The table is like, there are many tables, so we're not able to present it here because it's a very big table. So we found that the average false acceptance rate for real actions is around 1.67%. And for imaginary actions, it's around 1.95% for left-hand actions and 0.83 for right-hand actions. And the average false rejection rate is lower than 20% for all actions. You might have seen that a false acceptance rate, a very low false acceptance rate, is much more critical than a false rejection rate, as the former leads to an access of the system to the wrong user, which later leads to requirements of more than one attempt during authentication. For example, we don't want the false acceptance rates to be a very huge value compared to the false rejection rate, as we don't want an imposter accessing a client. So this is where the real problem happens. I mean, it's fine if the client is not able to access the system, or if the system recognizes it as an imposter, but it's a major, huge problem if the imposter if the system recognizes an imposter as a client, as it can lead to security breaches and other concerns. So as you can see, the false acceptance range is very low, 1.67%. So it's a very good value that we have achieved for our system. So now we're talking about the multimodal approach that we used in addition to the other models that we used. Hence, we found that a participant that performs well over one action may not perform well the other action. Therefore, no single action shows the best accuracy over all the tensor subjects. Therefore, it is evident that the actions have an impact on the system performance. And the best performing action varies on subject to subject basis. This results support the approach of building a multi-model system that combines the different actions to design a more reliable and secure authentication protocol. So in this set, we proposed three such multimodal systems that combine all the 8 actions. And so we used three models. One was combining only the imaginary actions. Second one was combining only the real actions. And the last one was combining all the actions. So the features extracted from each of the sets were fed into respective random forest classifiers, and 8 classification outputs were obtained, and the system's final output being the mode of these outputs. So what I'm trying to say from this is that we took the features of the user and we then put it into the random forest and we saw the output. And for example, if it's subject 7, and if the random forest gave the output as the subject 7 itself, that means it's able to predict that the person is 7 itself. But if it predicts another person, that means it's giving a false negative, false positive. So in this case, we took the mode of it. For example, there are 10 outputs and it gives 7 around 8 times. That means we took the total output 7 since this was the most relevant value. And now we're talking about the limitations and the future work. So first one would be the diversity of the participants. The study that we conducted was very limited in the diversity of the participants, and it was very limited to specific age group, and further analysis of different age groups is needed so that we can give a better comprehensive detailed analysis of a study. And another important problem was that most of the participants were right-handed, and we need a more diverse set would have been much better in creating a much better model, since in this case there'll be a slight bias towards the right-handed people than compared to the left-handed people. And cost reduction, which is an important part of any authentication system, because you don't want the cost of the system to be like exponential. So in this case, the recording was done using 32 channels, and we noticed that only 4 channels are really necessary. So the rest 28 channels were redundant. So this leads to an unnecessary extra cost of the headset. And for commercial applications, we plan to develop a 4-channel system that's able to like reduce the cost very significantly, and this also helps in even giving it some marketing and even propose it to consumers. And our next study would be integrating the biometric that we use with other biometrics like fingerprint, iris, or a face detection system to build a more secure biometric system, as no biometric system is perfect. Hence, combining different biometric system can help us give us more security and helps in preventing security breaches. So, thank you.